Welcome to G Fun Facts Online. Today we're going to Mars, a planet that, at first glance, seems like a vast, static, rust-colored desert. But if you look closer, especially at its polar regions, you'll find that a silent, powerful artist is at work, sculpting the landscape in ways that are truly alien. This artist isn't wind or water. It's sublimating carbon dioxide. And its most spectacular creations are bizarre, web-like patterns etched into the ground, known to scientists as landforms, but which everyone else calls Martian spiders. These intricate networks of troughs tell a story of seasonal change, powerful geysers of gas, and a climate system fundamentally different from our own. This is the world of sublimation geomorphology, a field that explores how the simple act of ice turning directly into gas can carve up an entire planet. To understand how something as ethereal as a gas can carve canyons, we first need to appreciate the profound seasonal changes that grip Mars. Like Earth, Mars has an axial tilt, which gives it distinct seasons, but its year is almost twice as long as ours, and its atmosphere is incredibly thin, over 95% carbon dioxide. This combination creates a dramatic seasonal cycle. During the long, dark polar winters, temperatures plummet to as low as minus 130 degrees Celsius. That's minus 200 Fahrenheit. It gets so cold that a huge chunk of the Martian atmosphere, as much as 30%, literally freezes out of the air and falls as snow, blanketing the poles in a seasonal cap of solid carbon dioxide or dry ice. This seasonal blanket can be up to a meter thick. As Martian spring arrives, the sun's rays return to the poles. But this isn't a gentle thaw. What happens next is a series of violent and transformative events. Unlike water ice, which melts into a liquid, dry ice on Mars undergoes sublimation. It turns directly from a solid into a gas. This phase transition is the engine that drives the planet's most exotic geological activity. For years, scientists were baffled by the strange, spider-like formations first seen in detail by the Mars Orbiter camera in the early 2000s. These landforms are networks of branching, dendritic troughs that can stretch from tens of meters to over a kilometer across. They looked like nothing on Earth. The leading explanation for how they form is called the Kiefer model, proposed by geophysicist Hugh Kiefer. It's a brilliant theory that paints a vivid picture of a uniquely Martian process. It all begins with a peculiar property of the seasonal dry ice cap. It's not opaque like water ice snow. It's translucent, like a cloudy piece of glass. As the spring sun gets higher in the sky, its light shines straight through this clear slab of CO2 ice and hits the dark soil underneath. This dark ground absorbs the solar energy and heats up, just like a dark car on a sunny day. The warming happens from the bottom up. This heat causes the base of the ice slab to sublay, turning directly into carbon dioxide gas. But this gas is now trapped. It's stuck between the cold, impermeable ice sheet above and the warming ground below. Pressure begins to build in a process known as the solid-state greenhouse effect. Eventually, that pressure becomes too much for the ice slab to contain. The gas finds a weak point in the ice, and with explosive force, it erupts. These are not gentle puffs of air. We're talking about geyser-like jets of CO2 gas that can reach speeds of up to 160 kilometers per hour, or 100 miles per hour. And these jets are not clean. They carry with them the dark sand and dust from the ground they were trapped against. This mixture of gas and dirt is blasted high into the thin Martian air. This explosive eruption has two major consequences for the landscape. First, as the gas rushes towards the vent, it erodes the ground underneath the ice, carving out a network of channels that all converge on that single weak point, the vent. Season after season, year after year, these eruptions happen at the same weak spots. The channels grow deeper, longer, and more complex, forming the intricate branching legs of the Martian spiders. The second consequence is what happens to all that material that gets blasted into the air. The heavier sand-sized particles fall back down to the surface pretty quickly, often forming dark circular spots or blotches on top of the ice right around the vent. The lighter dust particles get carried further by the Martian wind, creating beautiful, fan-shaped deposits that can stretch for tens of meters. These dark fans are the smoking gun, a telltale sign of recent or ongoing geyser activity. Once spring and summer are in full swing, the entire seasonal CO2 ice cap sublimates away into the atmosphere, revealing the ghostly, spider-like patterns that were carved into the ground beneath. The dark fans and spots disappear with the ice, but the channels remain as a permanent record of the violent, gas-powered erosion that took place. While the classic spiderweb ionoforms are the most famous, these CO2 geysers create a whole zoo of different landforms. Detailed images from the HiRISE camera on NASA's Mars Reconnaissance Orbiter have shown that not all spiders are the same. Scientists have categorized them based on their appearance. There are fat spiders, with wider, more rounded troughs. There are thin spiders, with long, slender, and winding channels. And there are incredible starburst spiders, which are huge, radially symmetric systems, with dozens of fine channels radiating out from a central point. These differences are likely due to local variations in the ground itself, things like the grain size of the soil, how cohesive it is, and the thickness of the ice above it. Lab experiments have even shown that finer-grained soil tends to produce more branched, complex patterns. The dark fans and spots that appear on the ice are the most direct, real-time evidence of these active geysers. By looking at the orientation of the fans, scientists can figure out which way the wind was blowing at the time of the eruption, providing valuable data for Martian meteorologists. But the weirdness doesn't stop there. Sublimating CO2 is also thought to be responsible for another strange feature: linear gullies on sand dunes. These are long, narrow channels running down the steep faces of dunes in the polar regions. For a while, some thought they might be carved by liquid water, but they form in the frigid Martian spring when water can't exist as a liquid. The leading theory is as cool as it is strange. Blocks of CO2 ice that form on the dune crests during winter break off in the spring and start to slide down. As a block of dry ice moves over the warmer sand, it sublimates rapidly from its base. This creates a cushion of CO2 gas that levitates the block, allowing it to glide downslope with almost no friction, exactly like an air hockey puck. As it glides, it carves a perfect channel in the sand. When it finally stops, it often sublimates away in place, leaving a small pit at the end of the gully. We have images showing these gullies appearing over the course of a single Martian year, which is incredibly strong evidence for this dry, dynamic process. While the CO2 geysers are the most dramatic example, sublimation is shaping Mars in other, more subtle ways, often involving water ice. Mars has vast deposits of water ice buried just beneath its surface, particularly in the mid to high latitudes. The slow, steady sublimation of this ice over geological time creates its own unique set of landforms. In regions like Utopia Planitia, the surface is covered with shallow, rimless depressions that have scalloped, almost cookie-cutter edges. These are called scalloped depressions. The idea is that they form when buried water ice gets exposed to the thin atmosphere, perhaps through a small crack in the surface. Over thousands of years, that ice slowly sublimates away, causing the ground above it to collapse and form a depression. These depressions often have a distinct asymmetry, with a steeper slope facing the pole and a gentler slope facing the equator. This is believed to be because the equator-facing slopes get more sunlight, leading to more sublimation and a more gradual collapse, and we know the ice is there. Radar instruments have confirmed the presence of vast quantities of subsurface water ice in these regions, some deposits containing as much water as Lake Superior. Another bizarre feature linked to sublimating water ice is called brain terrain, and yes, it looks exactly like it sounds. A complex, labyrinthine pattern of ridges and troughs that resembles the wrinkled surface of a human brain. It's often found on what are thought to be Martian glaciers, mixtures of rock and ice. While its formation isn't fully understood, it's widely believed to start with cracks forming in an ice-rich surface. As the buried ice slowly sublimates and escapes as vapor, the ground settles and collapses, creating this intricate, folded pattern. These processes aren't constant. They are tied to Mars' long-term climate cycles. Unlike Earth, whose tilt is stabilized by our large moon, Mars' axial tilt or obliquity wobbles chaotically over hundreds of thousands of years. It swings from as low as 15 degrees to as high as 35 degrees. When the tilt is high, the poles get more direct sunlight. This causes massive amounts of water ice to sublimate from the polar caps. This water vapor then travels to lower latitudes and gets deposited as snow, creating extensive ice sheets in the mid-latitudes. The vast ice deposits we see evidence of today, the ones forming scalloped and brain terrain, are likely relics of these past Martian ice ages. Similarly, the largest and most complex spider formations may have formed during past eras when a thicker seasonal CO2 cap led to even more powerful geyser eruptions. So, how can we be so sure about these explosive alien processes? We can't go there and watch them happen up close, at least not yet. So scientists have gotten creative, using lab experiments and earthly analogs. At NASA's Jet Propulsion Laboratory, they built a wine barrel-sized vacuum chamber called Dusty. It's designed to recreate the frigid, low-pressure conditions of the Martian poles. In a series of amazing experiments, they cooled down a sample of simulated Martian soil, condensed a translucent layer of CO2 ice on top, and then heated the soil from below, simulating the spring sun. And the results were spectacular. They watched as pressure built up, the ice cracked, and plumes of gas and dust erupted, carving out miniature spider-like patterns in the soil. It was the first direct, physical proof that the Kiefer model works. Back on Earth, scientists have also found landscapes that share intriguing similarities. One of the most promising is the Qaidam Basin on the Tibetan Plateau in China. It's a high-altitude desert, one of the driest and coldest places on Earth. And there, researchers have found dendritic branching channel networks that look remarkably like Martian araniforms. Now, these are formed by a different process: upwelling salt water, not sublimating CO2. But the fact that such a similar pattern can be formed by an erosional process gives us valuable insight into the underlying physics. The study of sublimation on Mars is about more than just cataloging weird landscapes. It's a window into the planet's dynamic climate and its ongoing geological activity. It has completely changed our view of Mars, from a dead, static world to a place of active, seasonal change. The intricate dance of freezing and sublimating gas, the violent eruptions of geysers, and the slow sculpting of the land by disappearing ice reveal a world that is very much alive, geologically speaking. These processes, so alien to our own planet, highlight the incredible diversity of ways a world can be shaped. As we continue to explore Mars with ever more advanced technology, the ghostly spiders of the South Pole and the wrinkled brain terrain of the mid-latitudes will undoubtedly reveal even more secrets. They are all pieces of a grand puzzle, and by fitting them together we get closer to understanding the history, the present, and maybe even the future of our enigmatic red neighbor.